Welcome back to our channel. I truly hope all of you are fine, healthy, and surrounded with goodness. Today, we are stepping into a topic that is both mysterious and one of the deepest puzzles of modern science. This topic is dark energy. Dark energy is not science fiction. It is a real idea, born from careful observations of the universe itself. Astronomers discovered it, not in a laboratory, but in the stars. Specifically, they were observing distant supernovae, those massive exploding stars that act like cosmic lighthouses. In the late 1990s, two research teams compared the brightness and distance of these supernovae. The results were shocking. Instead of slowing down, the universe was expanding faster, as if something unseen was pushing galaxies apart. That mysterious push was given the name dark energy. It is called dark, not because it is evil or dangerous, but simply because we cannot see it, and we do not fully understand it. Imagine blowing up a balloon. Normally, if you stop blowing, the balloon's stretch slows down. But with dark energy, it's like the balloon is stretching faster and faster, all by itself. Scientists believe dark energy makes up about 70% of the entire cosmos. That means most of reality is something we cannot directly detect, yet it shapes the universe at the grandest scale. Some theories suggest it could be connected to the energy of empty space, also called the vacuum energy. Others suggest it might be a completely new field that we have not yet discovered. Whatever it is, dark energy challenges our understanding of gravity, space, and even the future of the cosmos. Before we move to our today, I want to say that this channel is user-friendly. No offensive content, no misinformation. We explain things with respect, curiosity, and authenticity. To understand dark energy more deeply, we must take a step back and look at the story of the universe. After the Big Bang, nearly 13.8 billion years ago, the universe was extremely hot, dense, and filled with radiation. Over time, matter began to clump together through the pull of gravity, forming galaxies, stars, and eventually planets. For a long time, scientists believed gravity would slowly slow down the universe's expansion. Just like when you throw a ball upward, gravity pulls it back down. They thought the cosmic expansion would gradually decelerate, but the discovery in the 1990s completely flipped that expectation. Instead of slowing, the galaxies were accelerating away from each other. This meant that something hidden, something invisible, was fighting against gravity. That something is what we now call dark energy. The most widely accepted explanation is that dark energy is related to what physicists call the cosmological constant. This idea was first suggested by Albert Einstein in 1917. He introduced it to make his equations of general relativity describe a universe that was static, not expanding, not contracting. Later, when expansion was discovered, Einstein called it his greatest blunder. But today, that same constant has returned in a new light because it may perfectly describe the effect of dark energy. Still, the mystery is far from solved. Some researchers suggest dark energy could be a dynamic energy field, changing with time, sometimes referred to as quintessence. Others wonder if our understanding of gravity itself needs modification. Perhaps the laws of gravity are not complete on cosmic scales. What makes dark energy so fascinating is this: it is not only invisible, but also untouchable. We cannot bottle it, measure it directly, or reproduce it in labs. We only see its fingerprints on the largest structures of the universe. Through cosmic microwave background radiation, through galaxy surveys, and through gravitational lensing studies, The hints of dark energy's influence become clearer. Yet the more evidence we gather, the stranger it appears. For example, why does dark energy have just the right strength to start dominating the universe in the present era? This puzzle is often called the cosmic coincidence problem. It is almost as if the universe has tuned itself in such a way that life emerges right around the same time, that dark energy takes control. Coincidence or hidden principle? No one knows for sure. The influence of dark energy is not just a small detail, it completely shapes the destiny of the universe. If dark energy continues at its current strength, the universe will keep expanding faster and faster for all eternity. Galaxies will drift farther apart, their light will fade, and eventually the night sky will grow darker and emptier. This scenario is known as the Big Freeze. In it, stars burn out, matter spreads thin, and the cosmos becomes a cold, silent space. But if dark energy were to grow even stronger, in the future, a more dramatic fate could await us. Scientists call this possibility the Big Rip. In the Big Rip, the expansion becomes so extreme that it overcomes all forms of attraction. First, galaxies are torn apart, then stars, then planets, and eventually even atoms themselves. Space itself would literally rip apart. On the other hand, if dark energy were to somehow weaken, gravity might once again take the lead. In that case, the universe could collapse back into a dense, hot state, a reversal known as the Big Crunch. This means the ultimate fate of everything we know depends on something we still cannot explain. It is both humbling and thrilling to realize that humanity is living in a cosmic mystery. What makes the study of dark energy even more remarkable is how researchers investigate it. They use massive sky surveys, mapping millions of galaxies, to trace how structures evolve over billions of years. They use advanced telescopes, like the Hubble Space Telescope and now the James Webb Space Telescope, to look deeper into space and time. They use instruments such as the Dark Energy Survey, the Sloan Digital Sky Survey, and the upcoming Euclid mission from the European Space Agency. Each of these projects collects precise data, measuring the shape of space, the bending of light, and the stretching of distances. It is a collaboration between astronomers, physicists, and engineers worldwide. And all of it is aimed at answering a single profound question. What is the true nature of dark energy? It is this question that keeps pushing science forward, because by solving it, we may not only understand the cosmos, but also uncover new physics beyond our current imagination. When we reflect on the mystery of dark energy, we see that it is not just a scientific curiosity. It represents the vast unknown, a reminder that the universe is larger, deeper, and more complex than our current tools can explain. The discovery of dark energy teaches us humility. It shows that even at the height of modern science, with satellites, supercomputers, and advanced equations, the cosmos still hides profound secrets. This mystery also connects to human imagination. For centuries, people looked at the stars and wondered about hidden forces shaping reality. Today, we continue that same tradition, but with evidence, mathematics, and collaboration across nations. What makes dark energy so inspiring is that it forces us to rethink the very framework of physics. Perhaps it is linked to quantum mechanics. Perhaps it reveals hidden dimensions of space and time. Or perhaps it is something beyond all theories so far, a brand new chapter waiting to be written. No matter what the answer becomes, the journey to uncover it is already changing Our understanding of existence, from the tiniest particles to the farthest galaxies, dark energy connects everything under one cosmic mystery. And while we may not yet hold the key, the effort to search brings out the best in human curiosity. It drives innovation, global cooperation, and a deeper awareness that we are part of something truly vast. All the information we provide comes from verified historical sources, including books, records, and archaeology, sources consulted for this topic. Chris Adam G. et al. Observational evidence from supernovae for an accelerating universe and a cosmological constant, the Astronomical Journal, 1998. Perlmutter, Sol, et al. Measurements of O and L from 42 high redshift supernovae, the Astrophysical Journal, 1999. European Space Agency, ESA, Euclid Mission Updates, 2023. LASA Dark Energy Overview, 2024. Friedman, Wendy L. Cosmology at a Crossroads, Nature Astronomy, 2017. Friends, thank you for joining me on this journey into the unseen force that shapes our cosmos. Don't forget to like, share, and subscribe to our YouTube channel, Thrones of Knowledge. And please press the bell icon so you get notified on time. Finally, we would love to hear your suggestions for our next topic in the comment section to make our shared experience even better